Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good day. Welcome back to my channel, Dr. Zulhilmi. Today we will discuss this new topic, which is analysis of structure. Okay, this is our second last topic, which is now in topic 12. Okay, so we have structure, and then the last one is the distributed force. Okay, so this will be your second last topic. But in this topic, we have three main components, which is a large topic. So we start by the first one here, which is trusses. Later on, we go to frame, and last one is the machine. Okay, we will see the similarity and the difference between these three one, which is trusses, frame, and machine. Actually, this trusses also is a part of frame, which is the frame and trusses is a structure where it is designed to support the load. The load given, it is the component, the structure is static, it just used to support the load. But the last one is the machine. It's used to support and transfer the load. Okay, to transfer. So there is movement to transfer the load to other point. Okay, so the first one here we see about the trusses. Okay, so trusses, I will go explanation here we have in our books. Okay, so we see a lot of structure that we call as trusses here in the construction of bridges, building, and so on. Okay, it is used because of it is really efficient to solve the engineering problem, and it is lightweight normally. Okay, and it can hold load from different angle. Okay, so that's why we use a lot of trusses. So in this book we explain that, okay, the trusses actually made up from what we call it, members with one connection and designed to support a load in one plane only. That's why we normally analyze in two dimension. Okay, it is end connection, members with end connection, meaning that we have trusses here. Normally, that even though we look at here a big component, but the trusses we consider as part by part. Like this one, we have this small part is one component. Okay, the other part here, for example, is another component. Here is another component. So the trusses is built up from several small linear component like this one. Okay, so another way we have this component, for example, just one bar, and combination of these several bar become a trusses. Okay, that's what we consider the trusses. Okay, all forces acting on a truss are considered to act at the connection at the joint. Mass of each members is also considered. Even though it is in relative connection between members and either welded or bolt, the members are considered at pin joint. In short, all members used in the construction of trusses are two force members. Okay, so in this case we consider, okay, we have this component, and this is the part where we join this component with other component, meaning that here we have one joint here we have a joint. Okay, and we consider the load given, the forces given will act on that joint, okay, through the that component, but will be at the end to that joint. And because of that, most of the case in here we will not consider the mass. Even though we will consider the mass, we put also the mass at the joint. So all the small component of the trusses is considered as two force member. Okay, two force member, we have, where you have seen the two force member is a member. There we have 2 point where we will have load force, which is one here and one here. The way we do it is just make a line between these two connecting point and force at this line of action at force. So FAB, for example, FAB, same force, opposite direction, same magnitude, but only opposite direction on the same line of action of force. So we consider that all the forces acting on members of the trusses is two force member. All is two force members. Okay, and then what else? So every members can either be in tension or in compression. In this way, what I've wrote here is in tension. If it is in compression, it's opposite direction. This is to be inward, and the other one is also inward, but must be same, only opposite direction. Okay. On the whole, solution of problem involves trusses are based on Newton's third law, which is action reaction. If you have force here, at the other point there will be another force, opposite direction, same opposite direction, same magnitude. So action reaction, Newton's third law. And then notice that in order to maintain equilibrium, unknown force of each member is opposite in the direction and at metal joint here. Okay, so we consider this in tension or in compression. Okay, so that is for trusses. So we have two methods to solve this one. Okay. Okay, so again, trusses, okay, made up from one simple component like this one, which is a two force member combined together to become a big structure. Okay, even though in the reality this point, okay, this joint is normally welded, fixed welded, but in our syllabus we considered that all the joint here what I've wrote, all the joint is a pin joint. Okay, all pin joint. Okay, all joint at the end of each part is a pin joint, meaning that there is no moment. Okay, all the forces only this one, which is a two force member without any moment. Okay, we consider all as a pin joint in the trusses. Okay, and again we have all the component is considered as a two force member. Okay, one force opposite direction, either in tension or in compression. Okay, so we have two methods, which is method by joint or method by section. Okay, we have two methods, which is method by joint or method by section to solve this one. Before we go to the method, let me explain. Let's say here we have this point A, which is this is B, C, D, E. Okay, so this is point A, this is point B, point C, D, E, for example. Okay, so when we want to analyze each component, we have to open up all the component. We will see that we have here, okay, as a one point, which is BA. The other one is another point, AC. Here we have another one, actually CA again, and here is another one down there, A and E. Okay, so this big part is actually made up from this 1, 2, 3, 4, 4 small component. Okay, and then join up together to become a single big structure. Okay, and when we open this one, we know that we have to put the reaction. So here, for example, here we have one component, and if I'm considering this one as in tension, so we have force this direction, same as here, force this direction, this all is two force member. Okay, this is in the structure, but also that we will have here the point that join together this component. We have one point, which is this point. Okay, and to draw this one, we have a Newton's third law, action reaction. This one this direction, so this one will go this one. This is opposite, this is opposite, this is also opposite at that point A. Okay, here is the free body diagram for the structure. Okay, the structure itself. This is for the joint, and you will see that if you combine, this one combine become 0, this one will become 0, this one 0, all will be at the end. There is nothing, no force here. There will be 0. Okay, but the force is a two force member followed Newton's third law, which is the action and reaction. Okay, so there is two ways here, method by joint and method by section. Method by joint is to look at in general, because we go detail later on. In general, method by joint is to look at this one. Okay, normally the question will ask you find or determine what is the force acting on this part, for example, these two parts. Okay, BA and also EA. Determine what is the force acting on that one, either it is on in tension or in compression. So you have to calculate. So the one way to do is to look at this joint. Okay, if you get the joint and you have this force one here and the other one here, you know that it is only opposite direction for this force. So meaning that if you know here, you know the force in that structure. Okay, if you know the force on the joint, you know the force on that structure. So the first one is method by joint. We analyze joint by joint, but by simple directly transferred to the other component, so you can know the force in the other component. The other method is method by section, where we analyze the component itself. Okay, we analyze the component itself. For example, we want the force here, so we do bisection, meaning that we have to put a section. Okay, so if I'm doing like this, meaning that I want to analyze this part, and this part. Okay, so this section I will analyze, so directly I will have the force here, here, and here. So depend. Some question will ask you to use both method to show that it is correct, or the other one will not set any method to you. You can choose which one, depend on the problem itself, how difficult it is. You once you do several exercises, you will see which one is faster or easier for you to be conducted. Okay, so there's two methods. That's how we go directly. We go to the detail of how to use these two methods. Before we go to the analysis, so first let me check this one, which is special loading condition. This one, special loading condition, you can see from your, okay, from here. Okay, this page, you have special loading condition. Okay, so you need to know this one because it will save you a lot of time during the calculation. If you know this special condition, you can directly eliminate some of the component, or you know directly which component is same force as the other component. So we go to this one, special loading condition. So to imagine this one, I have built this one, this simple part. For example, the first one, which is we have two parts, which is AB and CD. Remember, this part is a pin joint and all is two force member. So in order to maintain this force in this direction, meaning that here, there must be something that pull this part this direction or this direction. If there is nothing, because of this pin joint, the component will not stay that this way. It will be bend or something, because it is a pin joint. Okay, we lose joint, so pin joint. If there is no force acting on that component, the component will not stay online by this one. So if we have two components, which is AC and BC, in order for this component to maintain on a line, okay, if the component we have two components. Okay, one in red, one in black, and both component is in one line of action of force, meaning that this is the line of action of force. Okay, for example, if you draw the free body diagram, you will see, because we always put it is in two force member and we put in tension, in compression, what we draw is here there will be one force here and the other one is one force here. Okay, so this is one force out here, one force out here. Okay, so this force we call it inside here. You have to remember, if you open this one, it will be only one component, so one force there, one force here. So this force is this part. Okay, so now if we are drawing like this one, we have this force is, we call it FAC. For example, this is FAB. Okay, so in order for this component to maintain in this position, like this one, sorry, okay, is I will have, if it is in same line like this one, okay, either this part or this part, but we have one line of action of force. Okay, so in order it to be in that direction, the force that pulling this direction must be same as the other force here. It is action, reaction, Newton's third law. So in other way, it will be FAB is equal to FAC. Okay, if it is not equal, it will not remain static. It will not in equilibrium. For example, if this one is opposite direction, but this force is bigger than this one, it will move the other direction. Okay, it will move the other direction. If it is not on same direction, for example, if this one is this direction, the other one is pulling down, so it will not remain this, but it will go down. But still, the force acting upward and downward will be same forces. At any condition, you will have same forces as long as this is in same line of action of force. Okay, so if we have two components but on same line of action of force, the force acting on that component is same force by the two ends. Okay, so second part here, if we have now four components. Okay, four components, but not just any four components. This is not the same as this one. Okay, you see, not same. The reason is it is combination of this one, combination of this, but we double the numbers. So we have two part of this one, which means that if we have four components, two of it at the same line of action of force, this one, the other two is on the same line of action of force. Okay, so we have to imagine this one. Maybe I put here, one here, and I have to pull. Oh, sorry. I should have another person to pull this direction, and the other one is will be. So we pull here, both up, the other one down here, and the other one is pulling this direction. Okay. So in order for this condition to be happen, okay, so the force acting on here must be same as the other part here. So the force, if you look at the free body diagram, it is actually, we will have force because it is two force member also. So the force is this way. So F, this one AD, F AE. The other component is this one. So we have force that direction, FAB, FAC. So in order for this condition to maintain in equilibrium, we must have FAC equal to FAB, only opposite direction, and FAD is equal to FAE, but opposite direction. Same magnitude, opposite direction. If it is not same, this one, if let's say this is bigger than this one, it will go opposite direction. Okay, if this part is not same as this one, it will not be in the same line of action. This one might turn the other direction, so this can be not same as this. But if this to be same line of action, FAC must be same as FAB, and this one is same as this one. If you understand this one, we just double the numbers for the other part. Okay, it is the first thing you need to really put in your mind. All this is a two force member. So the force acting on that component is either in tension or in compression. All this one, I'm drawing it in tension first. Okay, so for this one we have same here. We have another two, okay, which is Here, this one is really critical during your analysis, because if you not understand these two, this one and these two, if you understand this one, you can eliminate a lot of unknown. Okay, you can eliminate a lot of unknown and save a lot of time. Okay, so I'm going to erase this one. Okay, now this one is, we have three components. One AB, BC, and AD. If AB and BC same line of action of force. If AB and BC is on the same line of action of force, I hope everybody get what I said when I said line of action of force. We have introduced this one in previous chapter. Let's say we have this force F. Okay, we make a line on this same line. On that line, this is what we call as line of action of force. Okay, so if AB and BC, we have three components. If two of it on the same line of action of force, meaning that here, okay, if two of it on the same line of action of force, the third one, which is AD, in this case, must be 0. Okay, remember, if we have three components, two of it on the same line of action of force, to maintain that component in the same line, the third one must be 0. Third one must be 0. Whatever the direction it is, the third one must be 0. For example, I have now this way, but here I have this way. Okay, these two is on the same line of action. Okay, first part and second part is same line. So the third part here, this one must be 0. Okay, the orientation, it doesn't matter, as long as two of it on the same line of action of force, the third one must be 0. So to demonstrate this one, let's say we have this. Okay, this one. Okay, we have these two force, and we have the other one, the third one. Okay, now looking from here, you see that this represents the force. I have force in the direction, I have force also in another direction here. Okay, other direction, so I have forces in these two directions. And I have the third one. And the third one here we see as we have 0 forces. What I mean is, if this component, okay, it's difficult to show, only one hand. So this one, let's say here, if it is on the same line of action of force, the third one will be 0. What happens if the third one is not 0? You will see that if I'm pulling here, okay, you will see directly these two will no longer be on the same action of force. It will be deformed. Okay, it will change. Doesn't matter which direction, it will change. Okay, it will be no longer on the same line. So in order to maintain here, I cannot put any force on this third component. So if I put, you see that they will be no longer in the same line. Okay, here represent this one. If I'm pulling here, they will be no longer on the same line of action of force. So that's why if there are three components, two of it on the same line of action of force, the third one must be 0. If that component is not 0, then this component will not stay on the same line of action of force. Okay, so three components. Remember, three components. But if we have three components, but here there is already another force F1, this rule cannot be used because there is another force that pushing or pulling. So this component cannot be used. This consideration cannot be used because there is another component, another force that is pushing. But we are talking about here only three forces. Three component meaning that three forces because we know it is a two force member. So three component, two in line, the third one must always be 0. There are some question in your in your exam that ask you determine where is the zero force member. So this is how you determine. Some didn't say to you, but it require you to determine forces in a lot of component. But in this component, there are several zero force member. If you know it directly, you can directly eliminate. Okay, this one is zero, this one is zero. Don't need to calculate. So you save a lot of time. So be prepared, or please take note on this one and do the exercise so that you're really familiar with this zero force member. Okay, the other one here. If we have two components now, if we have two components and both not on the same line of action of force, meaning that this is in this line of action of force, this is this line of action of force. So meaning that we have two components, both not on the same line of action of force. How this happen? Okay, we have these two components and we have no forces pulling or pushing, so it can be not on the same line of action of force. If I'm pulling this component straightly, you can see that it is on the same line of action of force. We come back to position 1 that I've shown previously, which is the force A equal to force B. Okay, so meaning that to have this condition happen, we have two components both not on the same line of action of force, we must have FAC equal to FAB equal to 0. Okay, this condition. If I'm putting any forces, they will directly go to the same line of action of force. Okay, so in order for this system maintain equilibrium in this direction, there must be no forces pushing or pulling. If there is forces, it will be straight, go to straight same line of action of force. So if you have two components, not same line of action of force, both components must be zero force. Okay, so these two cases we call it as a zero force members. Okay, so meaning that the forces, the component that not exert any force at that specific condition. Okay, at that specific condition, because if you see that in the structure there is a lot of structure and there is several components that not exert any forces, we call it as zero force member. So some of you will ask why we maintain this component. It not exert any forces, but why this component is there? We should directly put it away. Okay, so the why we still maintain that component is because only because at that specific condition, a specific loading condition, that component didn't absorb any forces, didn't have any forces. But if the load come from different angle, that component will function. Okay, that's why we have trusses. Okay, but for that specific component only, the force is not there. But if the load come from different angle, maybe the component will take action and that component will transfer the force. That's why we will not eliminate the component. First one, because of the to cater different type of loading, okay, different type of condition loading, and to maintain the structure of the trusses itself. So there's two big why we maintain the zero force member on inside the structure itself. Okay, so we do some exercise to determine the zero force member from several example here later on. Okay, so let's see. Okay, so let's see this several example determine zero force member in this tree structure. Okay, we look at the first one, zero force member. So remember that for the zero force member, we have to have three components, both two of it in the same line of action of force. The third one must be zero. Or if you have this kind of thing, there are two forces, two members, but both not in same line of action of force. So the both of it must be zero forces. Okay, so we call it as zero force member. So we look at one by one from here. Maybe this one we have one component. So remember that all here is the joint, the pin joint here. All is joint, pin joint, not one rigid body. So the trusses, it is not one big rigid body, but combination of several simple beam joined by pin joint to become a trusses. Okay, so look at this one. If you look at this one, you can see here it is same as this one. but in this case we cannot put it as zero force member because we have another force P. Okay, in order for this one to become both zero forces, there must be no external forces. For here we have one external force acting on this component, so this component cannot be zero. Okay, but now look at this part now. So we have these two, 1, 2 in line, and the third one here is not on the line, so this one is 0. Okay, so now from the beginning, here we have 1, 2, 3, 4 component, but since we have eliminated this one, so now it become one here same line, the other one is here which is not in line, so this one is already eliminated, so this one, the third one here is also 0. Okay, so I have eliminated 2 parts from here. Okay, even if you calculate from your analysis, you will find out that the force inside these two is equal to 0, meaning that the load will not go to that component, it will go directly to this one, and this one transferred to the joint. Okay, it will not go to this component. It will not. In this case, these two components have no function at all to exert any forces. Okay, so we look at this part. This part now we have 1, 2, and 3, but there's none of it in line. So this one in this direction, this one is here, the other one is here. So none of it is in line. So this 3 part cannot be a zero force member. Okay, so you have to leave it as this one. Here we see here we have 1, 2, 3, and 4 components. So it cannot be a zero force member. 2 not in line, only 2 in line. So not zero force member. From here we have 1, 2, 3. So we have 1, 2, 3, 4, 5. So no. Here we have 1, 2, 3, 4. So cannot be a zero force member. Here we have 3, but none of it on the same line of actional force, cannot be. So here we have these two, same as this one, but we have another part that hold the component there down, so it cannot also be 0. Okay, so we have only 2 parts, which is a zero force member here. Looking at this one, this end, we have another force, this part, okay, can be that one, but because of this force now, this one cannot be 0. If there's no forces, no force P2, this 2 is 0. But in this case, we have the force P, so this 2 is not 0. Okay, so look at this part, we have 1, 2, 3, 4, and 5 from here. So no question on that, not zero force member. But looking from here, we have 1, 2, 3, and this 2 is in line, this one is 0. Okay, this one is 0. Now look at this one, we have 1, 2, 3, 4, so no question. Here maintain 1, 2, 3, 4. Here we have 1, 2, 3, and 4, so no question. Here we have 1, 2, 3, and the other one is roller here. So down here 1 and 2 like that one, but we have the one pin that hold to the structure, so it is not a zero force member. The force will be transferred to that structure. Actually the force from here, okay, will be transferred to one here at the end and the other one at the end. So there is not a zero force member at that point. Okay, so only one which is zero force member here because of this part. Okay, so the other one here, you can see. Okay, so we have this one, 1, 2, 3, 4 point. 2, 3, 4, so cannot be zero force member. 1, 2, 3, 4. This is 1, 2, 3, 4. If you look at from this angle, it will all this cannot be a zero force member. But if I'm starting from here, okay, because I still not analyze this one, this 2 is in line, the other part is not in line, so this one is a zero force member actually. Okay, so this one is 0. Now, once I have already eliminated this one become 2, 1, 2, and 3. So this one is in line, the other one is not. So this one also a zero force member. So be careful where you analyze. You have to analyze all the components. Maybe if you look at only that part, it is not a zero force member. if you forgot to analyze one point, so you have to analyze all the point. So starting from here, you see that it is 0. Now I have eliminate here. This one will become 1, 2, and 3. So this one also is a 0. Now at this part we have 1, 2, and 3. So this one is also a 0. So we have 1, 2, 3, 4. 4 part which is actually a 0 first member. In other way, actually, okay, what happened is the load from here, we have 2 load here, which is T1, which is also T1 mg. This load will be transferred directly to this point. So the load from here will go directly to this point and this point. Will not be catered by these 2 points. Yeah, 1, 2, 3, 4 other component. Okay, the load will not pass through here. It will go directly from here to this point, and the other one to this point. But we still maintain the structure, because if this component receive load from other direction, it might have some forces inside that component. But in this case, this 4 force component will not exert any load. The load in here, the force here will be equal to 0. If you analyze, if you calculate, given mass is something, so you calculate the T and you do the analysis, you will find that here it must be 0. Okay, that's why we call it as a simple 0 force member. We have identified this one, and then you don't have to calculate by just identify looking from the figure and the case. You can directly say, okay, the load here will be 0. Even though if you calculate later, lastly the load will become 0. Okay, that's it for 0 force member. So at the end of this video, you should be able to see from the figure, look at example, and determine the 0 force members in that structure. Okay, so thank you. See you next video for analysis of structure of trusses. So we do both method, which is method by joint and also method by section, in our next video. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.